What if I tell you that everything around you is mostly energy? Every bird you've ever heard, every loved one you've ever hugged or kissed, me, you, we are all made up by 17 particles that interact with each other through the emptiness of space. Now, it may sound hard to believe, but it is the foundation of existence itself. Atoms, the building blocks of everything, are mostly empty space. But the distances between its components are actually not so empty as it seems, but filled with those quantum fluctuations. Quantum fields which have potential energy to create new pairs of matter-antimatter particles. Most of those particles annihilate themselves right after popping into existence, but something odd occurs in the atomic core. These fluctuations are being cleared out. When you are binding stuff together, you are forcing them together, and in a process, losing energy. This is exactly what happens in the subparticles. As I said in my previous video, the bosons are in charge of telling the rest of the elementary particles how they could act according to the four fundamental forces. The gluon field and boson are responsible for the strong force that binds the quarks. The existence of the quarks itself suppresses the gluon field and creates what we call a flux tube. Now, as I said earlier, energy is needed to clear out the space. Where does it come from? Well, quarks are not static. They're constantly moving with the gluon field and have kinetic energy because of it. If you put enough energy, the flux tube will become longer and longer and longer, but if you have put enough energy, you might create a new pair of quarks. So, in a proton, for example, you can have any odd number of quarks, as long as they're all bound together. But what has all of this to do with everything being mostly energy? Well, physics' most famous equation could actually answer the question, but only if we rearrange it. We can get an amount of mass if there is lots of energy. The rest mass of the quark is 2000 times less than that of the proton, but the proton weighs more because of the kinetic energy of the quark. The same exact thing happens to the leptons and the electron, but here the Higgs field also plays a big role. Thank you so much for watching. I hope you found this video helpful, and if you have more questions, you could actually check our previous video. Thank you, bye!